We can start our session today, and today we have a speaker, Mykola Vovchanskii, with a talk on the rate of convergence for the fractional step method for Arratia flow. Please. Oh, we cannot hear you. Коля.
Звук. Oh, I'm sorry.
Okay, you can start.
I didn't unmute myself and was struggling to find where to unmute it. What I'm going to talk about today is a part of my PhD thesis defended recently, and it was done under the supervision of Professor Dorogovtsev. So I start with a brief reminder of what the Brownian web is. So we have a collection of random processes, which are Wiener processes, moving from every point of the real line at any positive time and coalescing upon coalescence, upon meeting. So first it was introduced by Arratia, and a modern formulation of the Brownian web as a random compact in a proper space was done in the second paper cited here. A question arises whether the Brownian web can be seen as a dynamical system, because it does possess this good property. And this holds for all U, S, T, and R, and with probability 1. However, if we ask about the proper definition of a dynamical system, there are some problems. For instance, Darling proposed a construction of a Brownian web. However, he lost joint measurability when we consider also the dependence on omega. And such attempts have been carried for some time, and up to the time it was the last paper is due to Riabo, where he obtained the Brownian web as a joint measurable mapping. However, right-left continuity with respect to the space variable is lost. Anyway, what we are going to discuss doesn't take into account such fine properties, because we still can think about Brownian web as a family of random mappings of the real line. So the question arises whether standard methods from the theory of random system are applicable in this case. And one of such standard methods is the fractional step method, also called the Cattoli-Trotter formula or the splitting. And this is a very brief reminder of what it is. So in the simplest case, we can solve the equation written here for x of t by combining semigroups corresponding to partial equations obtained by decomposing the drift present in the equation into simpler ones.
Sorry for interruption, but I would like to make a remark that some specialists say that this is the Daletsky-Lee-Trotter formula, not Cattoli-Trotter formula.
Yes, exactly. It was my remark too. Yeah.
Okay.
I haven't seen actually this formulation. I have seen this one, Cattoli-Trotter formula. Possibly there are Daletsky-Cattoli-Trotter or Cattoli-Lee-Trotter formulations. I just haven't seen them.
So I have never seen Cato in this context, but this is the Lee-Trotter formula, known in the West as Lee-Trotter formula. But Dr. Children of Daletsky say that Daletsky has done the same independently from Trotter, and so this is Daletsky-Lee-Trotter formula.
Yeah, this may be possible. For instance, the well-known expectation maximization algorithm was done by the Ukrainian mathematician, but nobody knows that. It's called EM, but it was done by Schlesinger. So I'm sorry if I mispronounce it, but I did see such formulations. In case of stochastic differential equations, where we have differentials of Wiener processes or even cylindrical Wiener processes, there are also results. And the first one, I believe, at least the first one I'm aware of, is the result of Benzo-San-Glavinsky's Raskaniu. Then it was generalized and deepened by Goncharuk and Kontelenets. And also I cited here Fou, where he obtained, in this paper, he obtained LP estimates of the divergence between the splitted process and the initial one. However, despite the fact that we are going to obtain some LP estimates, they are different from those obtained by him. And in the context of SPDEs, one can look for works of Krylov and Kosers and other people. The framework we are dealing with sounds as follows. We consider a bounded Lipschitz continuous function, consider the corresponding solution to the simple differential equation, consider the sequence of partitions of the interval 1, 0 with the size of the partitions going to 0, converging to 0. And we defined in a standard way our splitted version of X, where phi is Brownian web. And essentially what we do in a standard way, we solve ordinary differential equation, then add some action of the Brownian web and repeat it, removing these parts. So what we obtain are some pieces of Brownian motions with jumps. And it was shown in the paper of Drogovtsev and Vovchanskii that if we consider Arratia flow with drift, we have convergence in the sense of finite dimensional distributions in the space of, in the product space of Skorokhod spaces. I think it doesn't matter which topology is considered, the product one or the topology on the product of the spaces. Here, the Arratia flow with drift is a system of Wiener of semi-martingales satisfying these stochastic differential equations that start at time 0 from the real line and again are independent and until a collision happens, and then they merge together. This notion was introduced by Drogovtsev in this measure-valued process of stochastic flows. And the natural question is, can we measure this, is whether we can measure the speed of convergence. And I want to present a scheme for obtaining such estimates by mimicking the idea of the joint paper of Drogovtsev and Fomichov, which I will cite later. So we consider the following framework. We start with the space of all probability measures with finite pith moments endowed with the Wasserstein metric, a standard Wasserstein metric. And then we consider the distributions on this space. So the probability measures on this space, this is our new space. And we introduce the induced Wasserstein metric in this very same way, but here we write the Wasserstein distance between these two probability measures. And we consider the images of the Lebesgue measure on the interval 0, 1 by the action of the Arratia flow with drift and our splitted process. And we estimate the Wasserstein distance between the distributions of such processes, such random measures. So essentially, this idea was proposed in the paper of Drogovtsev and Fomichov, the rate of weak convergence of the endpoint motions of Harris flows from 2016. And it is formulated for Harris flows, and the Harris flow is a collection of correlated coalescent martingales. And it does, for what follows, it doesn't matter what the Harris flow is exactly. But what is important is the method of the proof. And using this method, it is possible to establish the following estimate. This theorem is strange in the sense that we have two logarithms. This is an extremely slow rate. It was published as the first and essentially the main part of this joint paper, 2020. And it's a shame that the formulation of theorem in this paper is missing the second logarithm. This constant Cp does depend on the function a, on p, and also on some specific parameter which can be fixed. So essentially there is dependence only on a and p. Now, the sequence of steps that we are going to discuss is as follows, and is essentially borrowed from the paper of Drogovts and Fomichov, though the realization and details are different. So firstly, we approximate our random measures with point measures, where we consider only trajectories starting from points j divided by m, where j from 0 to m, or m minus 1. Then we estimate that the error we get by introducing such approximations as discretization is small in the term of the finite metric. Now, the second step is to construct a suitable coupling for random measures, which is simpler. It is simpler to do than to introduce the coupling for the initial measures. Then we will estimate this distance, and at the last step, we will combine everything together. However, to proceed, we will need some LP estimates for the splitting procedure for the fractional step method. So now I will switch to that. I will start with rewriting the splitting procedure in the sense that if we have this stochastic differential equation dxt equals a of x dt plus dw2, where w is the Wiener process, we can define yn and zn as its splitted counterparts, where this is a stochastic part and this is smooth, piecewise smooth function. Of course, this is not the only possible way to do the splitting. One can, for instance, put t in here and this move here and so on. So there are 4 possible ways even to do that, but we will call that the splitting, possibly even abusing English, but since I am not a native speaker, I think it's I can allow that myself. And we will introduce the following notation. The solution of the stochastic differential equation with respect to the Wiener process, W that starts at t, we will denote as x equals d of w and u. And the splitting obtained, we will denote as s of n of w of u. So the first estimate we will need out of 3 is a simple generalization of the corollary in Bensoussan-Glavinsky and Raskine. Here we have expectation and supreme. Here we have supreme and then expectation, and this is important. The second lemma gives an estimate for the divergence between 2 solutions of stochastic differential equations that start pretty close to one to another, and theta here is the moment they meet. So the proof is pretty straightforward. However, since it exploits the same idea that is going to be used in the proof of the third lemma, I will give a brief sketch of the proof. So the idea is as follows. We introduce new process d eta, which can be found explicitly in this form. or in this form, where beta is some Wiener process. This is just the Knight theorem. And then we look at the difference between eta t and delta x. And it's easy to check using the property of aces of A that for those t that are less or than or equal to theta, eta measurizes delta xt. And then that means that we have this relation. So expectation of the supremum of this difference up to the power p is less than the expectation of the supremum of the process eta, where t is from 1 to kappa, where kappa is the first moment eta reaches 0. And the distribution of the stopping time can be calculated explicitly. So this is the formula, and then we obtain this estimate. This is a rough estimate, but it will be sufficient for our needs because those iterated logarithm comes not from the roughness of this estimate, but from the method used to prove the main result. So of course, for instance, the expectation of the kappa to the power 1/2 is like logarithm delta u minus per delta. So it's much smaller than delta to the power 1/2. But it's sufficient for us. To obtain the third lemma, we will need to introduce some modification of the splitting procedure. We allow the processes y and z to start not at point y, but at some point u, y and uz, which aren't required to be equal. And we will write this by introducing new notation, adding instead of u our new 2 points. And then we have this cumbersome result. So we additionally assume that this is bounded, but this is a reasonable condition, obviously. We have 2 Wiener processes, standard. We consider just splitting obtained by using these Wiener processes and these new start points. And then for any p and any fixed epsilon, there is c, which depends on p and epsilon, such that the divergence between these stochastic parts of the splitting up to the moment s, when we stop them at the moment they meet, can be estimated with this expression. Here is a strange term, but again, it is sufficient for our needs. Let me give us the sketch of the proof. So again, we introduce some differences of the initial points for the process y, differences for the initial points for the process z, difference of the processes y, and mi is just the supremum of I of function a, which is now finite. Again, we introduce the same process eta. However, now when we try to obtain the difference between, to consider the difference between delta y and eta, we obtain a good term and some correction, which is random. It can be estimated in some sense due to some technical and obvious relations. So essentially, we arrive at this where we have this difference of the starting points, which is going to be left in the final result. This is the estimate in terms of delta n. This is also can be estimated because this is just a standard Lebesgue integral. And here's the random part. As a result, by using the Bernoulli-Bellman lemma, we obtain this. where xi g is for g from 1 to n are independent and centered Gaussian variables with bounded covariance. So we, by the Levy inequality, have estimates on the maximum of the taken to the power p, and for the probability that this maximum reaches is greater than some fixed xn. So at the same time, using the previous calculations, we obtain the estimate on the supremum for all z less than or equal to theta n, in terms of the supremum of eta, but now we consider this supremum over the not over the interval from 0 to kappa, but from 0 to eta n. And therefore, we obtain the expectation of this theta n. However, we can notice that at this moment, this should hold. This is just because delta y theta n equals 0. So if you take special xn, we can estimate this in the following way. This is a sum of two summands. The first one is the probability that this correction gets big, and the second summand is just the expectation of the moment the process eta hits this level, deterministic level, which again can be calculated explicitly. So gathering everything together, we arrive at the conclusion. Now we are ready to produce the coupling, and let us recall that we consider mu n m and mu t m as the discretized versions of the initial random measures. And we build coupling for x's in a very standard and expected way. We just run independent copies of Wiener processes, obtain some solutions, and merge them upon a collision. So we introduce the moment our x meets some x in the system of new coalescing x's with a number that is smaller than g. So theta g is the first moment xj meets x1 tilde, xj minus 1 tilde, which are already coalescing by construction. And theta and g is the first moment this meeting happens for y's. And we do the very same for y's. We allow them to live until they meet, and then we merge them together. However, for z tilde g, we should apply a bit different. This apply a strategy that is a bit different. So if we have some interval in our partition where while our y's meet, we allow that g tilde live as that g up to the right end of this interval, and only then we switch to our new z tilde nj minus 1. For this to make sense, we also need to introduce new Wiener processes. The first one for x's, and the second one is for y's and z's.
Excuse me, it will be much more clear, maybe if you can draw a picture just for case when we have two starting point in the partition, and how we actually do this coupling.
So we do the coupling as follows. So suppose we have just y1, y2. We have our y1, y2, which is of this form. Then we find the first time they meet. So this is our y1, this is our y2. So now y2 tilde starts equal to y1 after this moment. So they merge here. At the same time, we have here some zeta1, z1, z2. They may be they may meet each other, they may cross each other, it doesn't matter. We do not change the two up to this moment of time. And only that we switch them to the tilde n with a smaller number.
So we allow them to change
only at this point of time.
Or only after y processes y.
Yes. Only after the interval where y's meet ends. So this is very related to the very definition, since it lives up to the right end of this interval. So we allow it to live because it, or here, because it uses the value of w, which
fixed value.
Yeah. So it uses vg tn with a smaller number. So, and if we do coupling in such a way, then we have these two representations. So xg tilde is the solution of stochastic differential equation with respect to wg tilde, and y tilde and z tilde and as the splitting, but with respect to a new Wiener process, which is different from this one.
So we also recalculate this Wiener process.
Yes, here. We just switch to the Wiener process with tilde and a smaller number at the same moment y's meet. So it's simpler than for that process. However, it does produce a coupling. It's easy to verify. So this is our Arratia flow with drift, and this is our xn. So the splitted version of the Brownian web. But the problem is that here we tilde j doesn't equal w tilde and g.
It was my my remark. Yeah.
They aren't equal, and this introduces some technical difficulties in the proof, but it can be done. So it's actually why we needed all these estimates, like this one especially. Now, the discretization error can be estimated pretty straightforwardly. So for that, one uses the very same calculation for the Rogowski and for Michov with some minor generalization. So we have a good control of it. And now we are ready to prove the main result. I will show it again. So the sustained distance between the distributions of the random measures, the first one being obtained by taking the image of the Lebesgue measure by the Brownian web as a second by the Arratia flow with drift, and the second one being obtained as the image of the Lebesgue measure under the action of the splitted version of the Brownian web, is measurized with this expression. Since the proof is lengthy and technical, I will give only main steps of the proof. So it's straightforward to obtain this estimate because this is a coupling. And now we should consider the distance in LP, usual LP norm over the omega space, between x tilde j and yn tilde j. Now one can introduce this decomposition of 1 into 4 different cases depending which place t is compared to theta k and theta nk. So theta k is the moment where xk and xk plus 1 meet, and this is a point where ynk and ynk plus 1 meet. And we will write it just by substituting, if it's possible, for x tilde and y tilde simple expressions. So here, for instance, we get something like this and so on. Yeah. Then, by taking the supremum over all s and taking mathematical expectation, we can simplify it into the sum of 4 summands. The first one is done. The second one is the same as the first one, but for the k that is less than k plus, that is less than k plus 1 by exactly 1. And the last two should be estimated by hand. So I introduce new function fp, which is sum of 1 and the first and the piece norm. And the main relations that we are going to obtain sounds as this. We have the recursive relation between the supremum over s of fp of the difference x k plus 1 minus y k plus 1 and both tilde in terms, and the same supremum, average supremum for xk and yk both tilde. This constant, if we check everything precisely, is greater than 1. To do this, we need to estimate these summands independently. And it can be done, but since it's a lengthy calculation, which is now pretty straightforward, I will just give an example, a partial example. So for instance, we arrive at this expression where we have some y with tilde and y at the next step, but without a tilde. And we can estimate it in terms of new splittings, which build for some Brownian processes and which start at this moment theta k. Here should be k, of course. And these Brownian motions are independent of this VEG. And tau 2 here is the moment this size meet. For other summands, it is needed to introduce, for instance, dw and g, u corresponding u, and so on. But it all goes down to some estimate of this type. Like, for instance, here, this is one of the differences we need to estimate. It came from here. So it should be k plus 1, k plus 1, k. So this is the difference that is appearing in the estimate for this expression if we apply the lemmata we proved previously. So again, it can be estimated in terms of 4 summands. And here we have the standard estimate, the first lemma. Here we also have the first lemma because now we have supremum here and then expectation here, expectation here, a supremum here. It's exactly as it was stated in the formulation of the first lemma. Here we have just the ordinary estimate for stochastic differential equations because this is the time it starts and this is the time when it starts, and this is the terminal point. And here we apply just the Gronow-Lebesgue lemma. And as a result, since we know how to start our recursive procedure, we can conclude with this estimate. So that's why epsilon was from 1 to 1/2. And gathering everything together, we can arrive at this estimate, where C is some constant that is greater than 1, so we cannot get rid of it easily. And we just need to fix some epsilon, for instance, 1/4, and choose M to be dependent on N and to be of this form. Now we can conclude in the sense that this is a very slow rate of convergence, and this is the result of the method that was used to prove this theorem. Because the main relation in this, and it is exactly the place our problems come from. But for that time, it was the best idea I was able to come up to the time. So possibly it can be done better, but I didn't know how to do that better. So this is what we have. Also, there is another question. When we speak about the splitting, the fractional step method, usually people ask about estimates in terms of normal some functional spaces. So this is another possibility for generalization of this result. And so I hope I will return to it one day. And all references were given during the talk, but this is just the repetition of them. That's all that I wanted to tell today.
Okay, thank you for the talk. Maybe somebody have questions or comments, please. I have several comments. First of all, if you show us maybe lemma 2, where you begin to use this Arrhenius-Uhlenbeck processes, yeah, yes, and it's proof actually. Here appears this eta t process. Here you use this difference W1 minus W2 minus W1. They're independent due to the construction of the Arratia flow. And in the future, you use the statement about the supremum of Gaussian, of the set of Gaussian random variables. So it seems to me that this result can be generalized to the Harris flow at least, because in this case we have the same as Slepian inequality, we have the same for martingales. So maybe the result can be translated to Harris flow. So at least the same rate of convergence can be obtained when we have not only independent up to the coalescent particles, but when they have some correlation.
Yeah, I thought about that, but I was unable to do it properly and quickly, and then I switched to another topic. But yes, this is what's been haunting me for some time, and I think it should be at least tried. Thank you.
Yeah. Also, it seems that this difficulty which came from the iteration of the estimation with the constant c, which you emphasized that constant c is greater than 1. I think that this is a technical moment, and at least we have to try another technique based on the real calculations of estimations of the related to point measures which are carried the flow. because right now we are working on this direction, and I think that in the future we can go back to the question of approximation of the image of the back measure by the fractional step method for Arratia flow with drift with almost different technique.
Oh, it's interesting. Because yes, it's a result of the application of the Burgholder-Zeves-Gandhi inequality and such rough estimates in this 2 to the power of p minus 1.
Yeah. Yes.
So it's technical.
Okay, then thank you again.
Thank you.
It remains to ask who will be the next speaker. Georgi, do you know?
Yes, you will be the next speaker.
Okay, so be careful. I will send to you the new title of my talk. Okay.
Of course.
Okay. Thanks everybody, and see you next week on my talk related to intermittency phenomena for visitation measures of random curves in random media. Okay. Bye.
Bye, everyone.
Thank you. Bye.
Thank
Bye.
you.